गुड मॉर्निंग स्टूडेंट्स। आपको मुबारक हो, आप सेकंड सेमेस्टर में आए हैं। तो आज हमारी पहली क्लास है सेकंड सेमेस्टर में, और मैंने इसका बैकग्राउंड आपको ऑलरेडी दे चुका हूं। मैंने आपको नोट्स भेजे हैं जिसमें मैट्रिसेस, उसके जो 12th में आपने पढ़ा है उसके बारे में आपको लिखा गया है हर एक चीज़। उसके बाद माइनर्स जो अभी मुझे चाहिए, माइनर क्या होता है। फिर मैंने आपको बोला था इसको जो मैट्रिसेस मैंने दी थी उसको जो विदाउट डायगोनल एलिमेंट्स है उनको ज़ीरो बनाना। आप ऊपर वाले एलिमेंट्स भी, डायगोनल के ऊपर जो एलिमेंट्स है उसको भी ज़ीरो बना सकते हैं। तो लोअर ट्रायंगुलर और अपर ट्रायंगुलर मैट्रिसेस बना सकते हैं। तो सबसे पहले जो हमें यहाँ सेकंड सेमेस्टर में सिलेबस है वो है मैट्रिसेस, फिर है पार्शियल डिफरेंशियल इक्वेशंस, फिर फोरियर सीरीज, एप्लीकेशन ऑफ पार्शियल डिफरेंशियल इक्वेशंस, एप्लीकेशंस ऑफ पार्शियल डिफरेंशियल इक्वेशन इसलिए फोरियर सीरीज के बाद क्योंकि ये फोरियर सीरीज इसके एप्लीकेशन में हमें यूज होता है। और फाइनली हमारे पास है integrals, surface and volume integrals, etc. So let me begin with matrices, and for matrices we have to begin with rank of a matrix. I assume that you know everything about matrices, whatever you have done so far in your 12th. Now matrices, what is matrix? Let A equal, this is the definition, let A equal Aij be a matrix of order m by n. If in this A there exists at least one minor of order R which is not equal to 0, whereas every minor of order R plus 1 in A is 0, then we say rank of A is equal to R, and we write symbolically rank A equal to R, or RA equal to R, or rho A equal to R. So if you have a matrix of order m by n, and in this matrix you have a minor of order R which is not equal to 0, whereas every minor of order R plus 1 in A is 0, then we say rank is equal to R. For example, if I have a matrix of order, you have a matrix A equal 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8. See, this is a matrix of order 3 by 4. You have a matrix of order m by n. Here order is m 3 by 4. Now you see, in this matrix you cannot have a minor of order 4, because for minor of order 4 you must be having a determinant of order 4. For determinant of order 4 you must be having 4 rows and 4 columns. You don't have 4 rows and 4 columns. You have only 3 rows and 4 columns, right? So you cannot have a minor of order 4. So rank of A cannot be 4. Okay. Now we have to see whether its rank is 3. For that we have to see that if there is at least one minor of order 3 which is not equal to 0. Now how many minors of order 3 are there? See, there are minors of order 3. Minors of order 3. How many are there? 1, 5. See, this one, this column and this column. This is one minor. 1, 2, 3, 5, 6, 7, 2, 4, 8. One minor. Another minor is again 1, 5, 2, 2, 6, 4. Then this one 4, 8, 8. Then again one more 2, 6, 4, 3, 7, 6, 4, 8, 8. 2, 6, 4, 3, 7, 6, 4, 8, 8. Then one more 3, 7, 6, 3, 7, 6, 4, 8, 8, and then 1, 5, 2. Now these are minors of order 3. All the minors of order 3. This is a minor of order 3, minor of order 3, minor of order 3, minor of order 3. Obtained from this matrix. This is the matrix of order. These are minors of order 3. And you can see every minor of order 3 in this matrix is 0. You can operate it. You can see its value is, every determinant is of order 3 is 0. So every minor of order 3 is 0. Because you see, you know, one of the properties of determinant that if you have two rows equal or two columns are equal, then value of the determinant is 0. This is 1, 2, 3. This again 1, 2, 3. This is 2, 4, 8. Sorry. 1, 2, 3, 2, 4, 6. Because we have taken this one 3, 7, 6. So 1, 2, 3, 2, 4, 6. 1, 2, 4, 2, 4, 8. Again this is 1, 2, 4. 2, 3, 6. This is 4, 6, 8. So this is 2, 3 and 4 again. Then 3, 4, 1. This is again 3, 4, 1. So all the minors of order 3 are equal to 0. So rank cannot be 3 even. So rank of A cannot be 3. So for 2 we have to see every minor of order 2. But if there is at least one minor of order 2 which is not equal to 0, then we say rank of A is 2. See, this is a minor of order 2. Its value is what? 1, 2, 5, 6. This is non-zero. So there is at least one minor of order 2 which is not equal to 0. Whereas every minor of order r plus 1 means 2 plus 1 is 0. 2 plus 1 means 3 also, 4 also. These are 0 and 4 doesn't exist. So we say rank of A is 2. Got it? Although there are so many minors of order 2 which are not equal to 0. This is a minor of order 2 which is not equal to 0. This is a minor of order 2 which is not equal to 0. This is a minor of order 2 which is not equal to 0. But there is at least one minor of order 2 which is not equal to 0. Therefore, we say rank of A is equal to 2. So, if in a matrix of order m by n, there is at least, this is very important, at least one minor of order r, here it is 2, which is not equal to 0, whereas every minor of order r plus 1, which is 2 plus 1, is A is equal to 0, then we say rank of A is equal to r, here it is 2. Okay, this is it. Now let me give you one more example. A equal 1, 2, 3, 4, 5, 6, 7, 8, 9. See, this is a matrix of order 3. Okay. Now there is a minor of order 3. Minor of order 3. Which is determinant of A itself. Which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me see what is the value. This is 1, 5 9s are 45, 6 8s are 48. Minus 2 into 36 minus 42. 4976 plus 3 into 48 32 minus 75 35. So this is equal 45 minus 48 is minus 3. 36 minus 42 is minus 6. So minus 6 into minus 2 is minus plus 12. Now this is 32 minus 35. This is minus 3. Minus 3 into 3 is minus 9. So minus 12 and plus 12, it is 0. So there is a minor of order 3 which is equal to 0. So rank cannot be 3. Rank of A is not equal to 3. Now, in order to find rank of rank of A, we have to see minors of order 2. And if there is at least one minor of order 2 which is not equal to 0, then we will say that rank of A is 2. You can see there is at least one minor. बहुत सारे minors हैं. There are so many minors of order 2. But there is at least one minor of order 2. 1, 2, 4, 5. Which is not equal to 0. This is 5 minus 8. This is not equal to 0. So rank of A is 2. Now let me go to the definition again. If A is a matrix of order m by n, if in A there is at least one minor of order 2 which is not equal to 0, whereas every minor of order 2 plus 1 is equal to 0, we say rank of A is 2. If in a matrix of order m by n there is at least one minor of order r which is not equal to 0, whereas every minor, there is only one minor of order 3 which is 0. So every minor of order 3 is 0. Every minor of order r plus 1 is 0. So rank is 2. Okay. Let me give you an example. One more example. Which will be a simpler one. A equal 1, 2, minus 1, 2, 4, minus 2, 3, 6, minus 3, 4, 8, minus 4. This is 4 by 3. 4 rows and 3 columns. Horizontal lines are known as rows and vertical lines are known as columns. You know everything about the matrices, its operations, its adjoint, its inverse, symmetry, secure symmetry, orthogonal, unitary, etc. You know that. Now, this is a matrix of order 4 by 3. Obviously, rank of A cannot be 4. Because minor of order 4 does not exist. We don't have a minor of order 4 over here. So, rank cannot be 4. We have to see minors of order 3 now. If there is at least one minor of order 3 which is not equal to 0, we will say rank is 3. But if every minor of order 3 will be 0, then we have to see whether there is at least one minor of order 2 which is not equal to 0. If that is not possible, then rank is 1. You can see it. You see, now minors of order 3. Minors of order 3 are, see, minors of order 3. This one and this one. 1, 2, minus 1, 2, 4, minus 2, 3, 6, minus 3. Another is 1, 2, minus 1, 2, 4, minus 2, and this one. 4, 8, minus 4. Then start from second row. 2, 4, minus 2, 3, 6, minus 3, 4, 8, minus 4. Then start from third. 3, 6, minus 3, 4, 8, minus 4, and 1, 2, minus 1. These are minors of order 3 from this matrix. You have a matrix of order m by n, 4 by 3. Rank of A cannot be 4. So we have to see whether there is a minor of order 3 which is not equal to 0. Now, these are the minors of order 3, and every minor of order 3 is equal to 0. What is the reason? The reason is that, you know, if there are determinants which have 2 rows or 2 columns equal, then value of the determinant is 0. You see, this is 1, 2, minus 1, this is again 1, 2, minus 1, this again 1, 2, minus 1. Same is the case over here, here, and here. So these are all 0. So rank of A cannot be 3. Minor of order 4 doesn't exist, so rank cannot be 4. Now there are minors of order 3. Every minor of order 3 is equal to 0. Every minor of order 3 equals 0. If there would have been at least one minor of order 3 which is not equal to 0, then we would have said that rank of A is 3. But every minor of order 3 is equal to 0. So we have to see whether there is a minor of order 2 now. Now minors of order 2. Minors of order 2. See, minors of order 2. 1, 2, 2, 4. 2, 4, 3, 6. 3, 6, 4, 8. And so on. 1, 2, 4, 8. Anything. 2 minus 1. 4, 8 minus 4. You have to take it respectively, corresponding. 2 minus 1. You can take 4 minus 2, 6 minus 3, 8 minus 4 along with. Okay. And there are so many minors. So many minors. Now you see, every minor of order 2 is 0. These are all 0. You see, this is 4, 1, 4, 2, 2, 4. 2, 6, 12, 3, 4, 12. 3, 8, 24, 6, 4, 24. 8, 1, 8, 4, 2, 8. 2, 4, 8, 2, 4, 8, 8, 1, 8. So every minor, there is not at least one minor which is of order 2 which is not equal to 0. So on. Every minor of order 2 is 0. So rank of A cannot be 2. Therefore, rank of A is equal to 1. Why 1? Because there is at least one minor of order 1. At least one minor order 1. Determinant of 1. Which is 1, which is not equal to 0. There is determinant of 2 also. Determinant of 6 also. Determinant of minus 4 also. Which is not equal to 0. But there is at least one minor of order 2 which is not equal to 0. So rank is equal to 2. Let me go to the definition again. You have a matrix of order m by n. Rank cannot be m because minor of order 4 doesn't exist. Now there are minors of order 3. Every minor of order 3 is 0. Now we have gone to minors of order 3. Now again every minor of order 2 is equal to 0. So rank is 1. Now let me come in reverse direction. Let A equal Aij be a matrix of order 4 by 3. Rank of A cannot be 4. There is at least one minor of order 1 which is not equal to 0. Whereas every minor of order r plus 1. R plus 1 here means 1 plus 1. Now it doesn't mean only 2. It means minors of order 2, minors of order 3, minors of order 4. Every minor of order 2 is 0. Every minor of order 3 is 0. So rank is 1. Got it? This is it. So you have, I know you have understood this rank concept. Now let me see. Now let me tell you, this is a matrix of order 4 by 3 and you were able to find, you were able to see that minor of order 4 doesn't exist. Then minors of order 3 are 0, minors of order 2 are 0 and minor of order 1 is obviously it is 1 and it is not equal to 0. And minor of order 1 does exist and it is not equal to 0, so rank is 1. Fine. Now you have to remember is that only 0 matrix has a 0 rank because you don't have a minor of order non-zero minor. Okay, there. Now if you have a matrix of order 10 by 10, this is quite difficult to find minors of order 10 first of all, whether it is 0 or non-zero. Say it is 0, then you have to see minors of order 9. So many minors of order 9. Then minors of order 8, 7, 6, 5, 4, 3, 2 and 1. This is very difficult. You cannot find so many minors, and there may be some minor of order say 8 which is not equal to 0, but you will see that or by mistake you have seen that it is it is equal to 0, and you will go to minus order 7, and so on. This is very difficult. So in order to find the rank of such matrices, 10 by 10, 100 by 100, what we do, we use elementary operations. So we can find rank of a matrix by using elementary operations. And you know what are elementary operations? Now let me tell you what are elementary operations. You already know, and I have given you notes also. Elementary operations. I will just let you know what these are because you already know that. There are 6 types of elementary transformations. 3 pertaining to rows and 3 to columns. I'll be sending some notes along with this video also. You can go through those. There will be definition extra. First is that you can interchange any 2 rows and columns also. So one is for row, one is for column. You can interchange rows and columns, and you know there is no change in the sign for matrices. However, for determinant you have a change in the sign. Okay. Second is multiplication. To any row or column, obviously, by a non-zero scalar. Say C1 plus lambda times C1, lambda times C2, column 2, lambda times column 3, lambda times column 4, lambda or k times row 1, k times row 2, k times row 3. This is multiplication by some non-zero constant. And third is addition of any 2 rows or columns. Addition of any 2 rows or columns. Addition means subtraction also. And obviously there will be multiplication of by non-zero constant also. Say C1 plus lambda times C2. C2 minus lambda times C3, or row 1 plus k times row 2, row 3 minus lambda times row 3, and so on. You have already gone through these phases and you have seen these things in your 12th class. So I will be just taking up questions finding the rows with the use of elementary operations. See, let me take up same exercises which we have done just now. You have 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, and 8. This is the matrix of order 3 by 4. You have seen that its rank is 2. Okay. Now what I have to do is that I have to make this 0 and this 0. Now let me operate row 2 minus 5 times row 1. A is equal to 1, 2, 3, and 4. I am operating through rows, so I will write row first. Row 2 minus 5 times 5 minus 5, it is 0. 6 minus 5 times 6 minus 10, it is minus 4. 7 minus 5, 3, 15, it is minus 8. 8 minus 5, 4, 20, it is minus 12. Right? Row 2 minus 5 times 5 minus 5, 6 minus 10, 7 minus 15, it is minus 8. 8 minus 20, it is minus 12. Then row 3 minus twice row 1. Row 3 minus twice row 1. 2 minus 2, 0. 4 minus twice, it is 0. 6 minus twice, 0. 8 minus twice, 0. As I have already said, these are 2 equal rows. This is 2 times same row. So therefore this will be 0. Now you can see rank cannot be, rank cannot be 4 because minus order 4 doesn't exist. So you can now see that rank cannot be 3 even because you know property of a determinant. If one of the rows or one of the columns of a determinant is equal to 0, then value of the determinant is 0. If you see rank a minor of order 3, in every minor of order 3, every minor, one row is 0. Whether you will take 1, 2, 3, 1, 2, 4, 2, 3, 4, 3, 4, 1, third row is 0. So its value is 0. So from this you can see that rank of A cannot be 4. Sorry, cannot be 3. So as per definition of the rank, if you have a matrix of order 3 by 2, m by n, and if in that matrix you have a minor of order r, at least one minor of order r, at least one, although there are so many, at least one minor of order r which is not equal to 0. This is the minor of order 1 which is not equal to 0, whereas every minor of order r plus 1 which is 3 or 4 is 0, we say rank is 2. You see, you cannot make this one 0. Whatever is in the diagonal, see, if you have a unit matrix is 1, 0, 0, 1. You cannot make diagonal 0, or you cannot use any operation by making any operation, and you cannot use any operation making these diagonals 0. So there's the diagonal minus 4. Minus 4 can be written as 1 because I can multiply this row by minus 1 by 4. This will be 1, 2 and 3. So, or 6, 1, 4 and 6, or 1, 4, 2, 8, 4, 3, no, 1, 2 and 3. So, this is a matrix, at least one minor of order r which is not equal to 0, which is of order 2 which is not equal to 0. So, rank is 2. So, rank of A cannot be 3 because every minor of order 3 is equal to 0. Okay, you see, because this rank is 0. This row is 0. There is at least one minor of order 2, at least one minor of order 2 which is not equal to 0. See this one, 2, 3, 4, minus 8. 2, 3, 4, minus 8. This minor, this is not equal to 0. This is 16 and 12. This is not equal to, so rank of A is 2. और हमने इससे पहले भी देखा था its rank is 2. So हमने एक और चीज देखी, elementary row or column transformation of a matrix do not alter the rank of a matrix. Rank जो होती है वो हो ही है, उसको change नहीं होता, कोई change नहीं होता है उसमें when you use elementary operations. Rank of a matrix does not, elementary transformation of a matrix does not change the rank of a matrix. Okay. Rank of a matrix remains unaltered, unchanged, whatever elementary transformations you will use. So rank is 2. Okay. Let me take one more example which I have already seen. What is that? A equal 1, 2, 3, 4, 5, 6, 7, 8, 9. You have seen that its rank is also 2. Again, its rank is 2. See, let me use elementary operation, make them 0. Operate row 2 minus 4 times row 1. Your A is 1, 2, 3. 4 minus 4, 0. 5 minus 4 to 8, minus 3. 6 minus 4, 3, 12, minus 6. Row 3 minus 7 times row 1. 7 minus 7, it is 0. 8 minus 7 to 14, it is minus 6. 9 minus 7 to 21, it is minus 12. Okay. Now you can make this 0 with the help of this. You can also make this 0 with the help of this. It's your choice. So operate row 3 minus row 2. Your A is 1, 2, 3, 0, minus 3, minus 6, 0, 0 and 0. Row 3 minus row 2, minus 6 plus 6, minus 12 plus 12. Okay. Which is 12. It is 2 times. row 3 minus 2 times row 2. 2, 3, 6. So this is 0. Obviously, you can see that rank of A cannot be 3 because there is a minor of order 3 which is equal to 0 because one row is 0. Now there is at least one minor of order 2 which is not equal to 0. You cannot make this 0. You can make, see, you can write twice 3, it is 6. 3 times 2 it is 6, but there will be 1. So you cannot make a diagonal element equal to 0. So rank of A cannot be 3. This is obvious because minor of order 3 exists, but this is 0. There is at least one minor of order 2. Minor of order 2. At least of order 2. What is that? Say this one. 2, 3, 3, 6 or 1, 2, 0, minus 3. Or 1, 3, 0, minus 6. Whatever you like. This is not equal to 0. So rank of A is 2. Fine? Okay. Now let me take another example which I have already discussed right now. Okay. What is that? A equal 1, 2, minus 1, 2, 4, minus 2, 3, 6, minus 3, 4, 8, minus 4. This is a matrix of order 4 by 3, and you have seen that rank of this matrix is 1. Let me take operations. Operation row 2 minus twice row 1, row 3 minus thrice row 1, row 4 minus 4 times row 1. What's A then? 1, 2 minus 1. This is 0, 0, 0, 0, 0, 0, 0, 0, 0. Fine? You can see minor of order 4, minor of order 3, minor of order 2. There is no minor of order 2 which is not equal to 0. Every minor, see, minor of order 4 doesn't exist. Now there are minors of order 3 which are all 0. There are minors of order 2 which are all 0. But there is at least one minor of order 2 of order 1 which is not equal to 0. So rank is 1. Fine? Rank of A is 1. I don't have to write all these things. Rank is 1. You see, you cannot take this thing. Minors of order 2 which are all 0. So rank is 1. Fine? You can also make, instead of row, you can take column transformation. Use column 2 minus twice column 1. You see, you can have column 2 minus column 1, 1, 0, 0, 0. Column 2 minus twice column 1, it is 0, 0, 0, 0. Column 3 plus column 1, this is 0, 0, 0, 0. See, you cannot make this one 0. This is in the diagonal. So, rank of A is 1. Because there is exactly one minor of order 1 which is not equal to 0. Fine? So, rank is 1. So, I think whatever questions I have given to you already in last week, and I will be sending few more for this session, you will be able to find rank by using elementary operations. Now, let me come to normal form of a matrix. Because it is related and it will be done here only. Normal form of a matrix. You see, if I have a matrix of order m by n, I have a matrix of order m by n. If I will use constantly so many elementary transformations, using elementary transformations, this matrix A equal to Aij of order m by n can be reduced to one of the following forms. One of the following forms known as the normal forms of a matrix. What are the columns, you can make a matrix in this form, IR only, or IR and 0, or IR and 0, or IR 0 0 0, where IR is a unit matrix of order R. Let A equal to Aij be a matrix of order M by N, and let me suppose that its rank is R. Rank of A is R. If rank of A is R, then you will get a unit matrix of order R. If rank is 2, you will get I2. If rank is 3, you will get I3. And if rank is 4, you will get I4. So if Aij is a matrix of order M by N, and which has rank R, and then using elementary operations, this matrix can be reduced in one of the following forms: IR, IR0, 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 0. These forms are known as normal forms of a matrix. IR is a unit matrix of order R, and zeros जो है, zeros are zero matrices. These are not simple zeros, matrices of different order. Different order. इनका order different है. This is known as partition. Okay, let me give an example. Simple examples. You see, A equal 1, 2, 3, 4, 5, 6, 7, 8, 9. You have seen that after operate row 2 minus 4 times row 1, row 3 minus 7 times row 1, I will get 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry. This is 0, this is minus 3, minus 6, this is 0, this is minus 6 and minus 12. I have just seen this. So row 2 minus 4 times 0, 5 minus 4 through 8, it is minus 3, 6 minus 4, 3, 12, it is minus 6. Similarly here. Now after making these two 0, I can make these two 0 and there will be no change in this. I can use column transformation using or operating column 2 minus twice column 1, column 3 minus thrice column 1. Your A is, I am using columns 0, 0, 0, minus 3, minus 6, 0, minus 6, minus 12. Because column 2, 2 minus 2, 3 minus twice 0, 4 times 0 or plus 4 times 0 will be 0, 6 minus and 0, minus 6 and 0, minus 12 and 0. Okay. Now I can make this one 0, this one 0 with the help of this. This I have already done in the previous question. So operate row 3 minus twice row 2. What I will get? I will get A equal 1, 0, 0. I am using row, so I have right row only. 0, minus 3, minus 6, 0, 0 and 0. Fine. Row 3 minus twice. Row 3 minus twice, this will be 0. Now I can make this one 0 with the help of this. So operate column 3 minus twice column 2. What I will get? A equal, again column 1, 0, 0, 0 minus 3, 0, 0, 0 and 0. Now finally I can operate minus 1 by 3 times row 2 or column 2, whatever you like. You will get A equal 1, 0, 0, 0, 1, 0, 0, 0, 0. Minus 3 into minus 1 by 3. So rank of A is 2. This is I2, 0, 0. Fine, rank is 2. What's the time? कितना हुआ time? 9 हो गया? Okay, I will take your leave now. Thank you.